All right, so your assignment number 3, I just released the solution earlier today. Take a look. If you got any trouble understanding about how the SLL node, the tree node work together in the solution, let me know and I'll be happy to help during the office hour. If you need some extra time from me, write an email or just reach out to me and then we can make up some time. For your programming test number 2, I'm going to release the guide and also example questions tomorrow, and also you can see the test date. And written test, programming test 1, the result and feedback have been released. If you got any concern, speak to me. I'll be also happy to talk. Just let me know. For your makeup lecture for the written test is on the cues, and pay special attention to something called circular array. It's a very interesting idea that you can actually get some insights about the array. You can take a look, and it's going to be covered in the exam eventually. And the notes template, office hour, TA contact, all the same, right? Any question about the course? Alrighty. Yes.
Sorry, thanks. So the schedule that office hours are also Friday, is that still the case?
Actually, no Friday, actually. Only Monday, Tuesday, Wednesday, Thursday, 3 to 4 p.m. Yeah.
Perfect.
Yes.
Programming test, you're going to stay on Tuesday?
Okay, that's a very good question. For now, guys, most likely you guys, programming test number 2 is going to be on a Tuesday, not Thursday, right? I will confirm when I release the guide tomorrow because we just don't have lab space for the Thursday evening, okay? But I'll definitely confirm tomorrow and then it's going to be fixed, okay? Alrighty, let's now do some recap and then we'll move on to the material, okay? Let's now, so last time we talked about the last 2 measures for binary tree. We're about external nodes and also internal nodes, about the lower bound and upper bound. You guys can review about the math and also about the visualization for each one of them, right? You want to be thorough about what's going on here. And also we spoke about the inductive mathematical induction on this particular problem here of proper binary tree. I would say take this lesson here more like a general pattern because the tree structure itself is recursive. It's very natural for you to apply mathematical induction on a recursive structure. So try to look at the base cases, try to look at inductive hypothesis, and also how we use the inductive hypothesis to prove about a general property, right? So that's really something you want to get used to. You might be asked question, maybe in the exam, to prove something around a similar level of difficulty, right? You want to get prepared for that. And we talk about one useful case for binary tree using the infix notation, but we also argue that it doesn't need to be proper if you want to support unary operator, right? That's also the discussion we had last time. And you want to look into the different traversal algorithm, right? We talk about pre-order, post-order, and also in-order. And just don't forget, for the in-order traversal, it has to be a binary tree. For general tree, with more than 2 child nodes, you just cannot do in-order traversal. By definition, you just cannot. And we talk about binary search, right? So you can definitely refer to the more details in the recording, but here is the essence. We're going to trace some example code, some example test case together with you to begin with. Given the entire array to begin with, you're basically going to directly to the middle. Because we know that the array is assumed to be sorted, it's a very important precondition for the binary search. If I know that the value I'm looking for is strictly less than the middle value, I know that I can safely just recur on the left-hand side. I can safely disregard the right-hand side. On the other hand, if I go to the middle value here, and somehow the key value I'm looking for is strictly larger than the v, then I can safely go to the right-hand side and safely disregard the left-hand side. We're going to see that today, mathematically, you can argue that this kind of going to the half and half, like this kind of pattern here, is going to be a much better efficiency compared with a linear search. That's something we'll see today. Okay? So you can review the idea about binary search, and then that's the Java code. I'm going to trace this code together with you today, but what you want to pay attention to is about how we use the from and to indices to specify the range of search space, right? In the beginning, we simply do from 0 all the way to the length minus 1. Basically from 0 all the way to length minus 1. And then in the middle, we have to go from either from middle minus 1, which will be the first half, the left half. Or you might go to middle plus 1 and 2, which will be the right half. You might go either way, but not both. So what you really want to pay attention to is about the if and else if. The syntax itself simply means you can either go for one branch, but you cannot go to both branches. So this will also impact the way you're going to calculate the running time later, right? I'm going to mention this insight again when I get there. All right, any question about binary search in general? All right, so I'm going to do some tracing with you. I'm going to assume you already got some familiarity about the code structure over here. So let's now do some test cases, okay? I will try to refer back to here when I need to, okay? So, oh, beg your pardon, over here. So let's now trace this particular input array. Let's say we're looking for the elements 18. As you can see, the one we're looking for does exist. It's right here. But let's see how we can use a binary search method or algorithm to actually search for that. Let's see exactly how it's going to go, okay? So we start with this public method here, simply search. That itself is not recursive, but it's going to call the recursive helper method binary search helper, right? So what we're looking for is the value 18 right here. That's the key that we're looking for, whether or not it should exist. If that exists, return true, otherwise return false. To really continue with the algorithm, we have to call the helper method. And what we do is we're going to specify the range of the search space. So the very first search space we're going to specify will be from 0 to 8. So if I just box this one here, 0 to 8, that one really corresponds to this particular search area, 0 to 8 right here. So this is what we call the initial search space, which is going to cover the entire array. This is the initial search space right here. All right, and then in each recursive call, we're going to do two things first before we call any further recursion. We want to know where the middle value is. First of all, we're going to calculate the middle index. Let me call it n. How do we calculate the middle? Because now it's from 0 all the way to 8. I can simply calculate average, which will be 4. That will be the middle. Okay? And will just be equal to 0 plus 8 divided by 2, which is equal to 4. That means I'm going to consider index 4 right here. And I'm going to use another one called middle value that's simply equal to A, the input array, at index 4. And that one there is simply going to be 15. Okay. So let me write a little better. So A4 is 15. All right. And now I want to compare this value over here against the key to see whether I should go to the left or right. Of course, you want to check to see whether 15 is equal to 18. It's not. So we're going to recur further. Okay. I can now do a very quick comparison. As you can see, the 18, which is the key I'm looking for, is larger than the 15, which is the middle value. That means I should go to the right, right? Because this is strictly larger than, so I know that I should really go to the right. So I should really go to the right. Right here. Okay. So you can think about conceptually, we're going to go to the right half right here. But how exactly do we specify the new range over here? As you can see, if you compare this initial range versus the right range, the ending index doesn't really change. We're going to change just the beginning index right here, right? Which would be 5, which is 4 plus 1, the middle index plus 1. So that's why you see here is 5, 8. Okay? So this is something you also want to make sure you got it. So this will be basically 4 plus 1, and then 8. And the 4 here correspond to the 4 right here. All right? So here you got 4 to 8. Sorry, 5 to 8 right here. Right? So this range over here corresponds to the right half that we're going to recur. So we kind of have the search space already for the first recursive call. All right, let's now continue. So now we got 5, 8 right here. We're going to continue with calculating the middle value. So you can see here, we got even number of elements over here. So when you actually calculate average, it's actually going to be around here. But that's okay. If you're just about 1 or minus 1 plus 1, asymptotically, it will still be the same. Okay. So let's now do the same step. So I'm just going to say the middle index is going to be, so go from 5 to 8. 5 plus 8 divided by 2. And if you use the division in Java by integer, it will just give you the quotient. So that'd be good enough, right? You don't need a double value. So 13 divided by 2, the quotient should be 6. That tells me I'm looking at index 6 right here. And the corresponding middle value should be 21. Okay, so A at index 6 would just be equal to 21, right? So now I'm trying to compare 21 against the key I'm looking for. Apparently, they are not equal to each other. So I should really do another recursion. Should I go to the left or should I go to the right? You got to compare these two values. So I'm going to write it down for you. So here you can think about the 18 I'm looking for is strictly less than 21, right? 18 I'm looking for is strictly less than 21. So that means I should go to the left. Conceptually, you should really consider the right-hand side right here, right? That's where I should go. I started with initial search space, and then I go to the right, and then I go to the left. That's basically what we're doing, okay? And this part here is actually going to be less than, so the conclusion is we go to the left. So you want to go to the left. More precisely, the index we're going to get is this. So we started with basically this range over here, and then the from index doesn't really change. But the to index should be the middle index minus 1. Okay, so what I have just shown to you, if you look at the Java code over here, we got from to middle minus 1. This one here corresponds to this one here. Oh, sorry, let me say it again. So this one here, we actually go to the right half. It will correspond to right here. Middle plus 1 and 2. That's something you want to find a correspondence. On the other hand, when we go to the left, right here, when we go to the left, right here, it's going to correspond to the from until middle minus 1. Okay, that's a correspondence you want to see. So what we get is, over here, we're going to get 5. And then the middle is 6. 6 minus 1. So this will give us 5, 5. 5, 5 is going to be exactly this range, just one element. And now we compare 18 against the 18. They match, so we're good. We found it. Okay. All right, so we can see the 5, 5 right here. So this will be the search space that we get. It's more like a base case as well. So now if you try A at index 5 equals 18, we have found it, so we're going to return true. True. That means we found it. And think about this case over here is one of the base cases. Let me show you again. If you look at one of the base cases when from is equal to 2, right? And then in which case we simply check to see whether the element in that index is equal to the key. In this case it is, so return true. All right, any question about this tracing here? So what you really want to notice about between each recursive call, how we narrow down the search space by half. That's really what you want to pay attention to. This one here, we are basically looking for the value 7, which does not exist in this array. So it should really return false. How do you trace it? Exercise. Okay. Give a try on tracing this example here. So I'll put exercise over here. You can give a try. So once you understand these two test cases, you can see one case for true and one case for false, right? To see exactly how binary search works. All right, any question? So until this part here, we basically completed discussion about binary search in Java. But now we want to move on a little bit further. We want to see what's the running time for binary search. You might know the answer already is log n, but we want to see exactly how to show it mathematically. Okay, so the idea would be, let me just give you a very quick preview. We're going to revisit the Java code right here, and then we're going to assign some mathematical running time function to it. It's called t. But I'll talk about t in just one moment. We're going to worry about the t, how to define that in different input sizes, and then we're going to solve that so-called recurrence relation. So there are two steps over here. Step number 1, we're going to formulate the Java code here into mathematical function. And step number 2, we're going to take that mathematical function and solve it and see what the running time is. Okay, so these are two steps. Let's do one at a time. Okay, and if you go back to the slides over here, let me show you there's some basic definition you want to take a look. Okay, okay, so now we are done with, oh, by the way, so for binary search, if the array is not sorted in that way, the best you can do is really do a linear search. Then we go back to 1021 or 1022. That'll be linear time at the worst. Okay? So the assumption about the input array being sorted is so important for you to do binary search. And that's the Java code, which we're still going to revisit when we formulate that mathematical function. So here, that's an important point here. We are defining a function called t. It's called a running time function. And then it's going to take a single input n. N will be the size of the list that we are trying to search for. It could be a list, could be an array, or it could be some linear collection, right? So that's going to be the size. So from here, let's now try to formulate that running time function, right? We're going to formulate it first, and then we're going to solve it, right? So that'll be the flow, right? We're going to focus on not this method specifically. That one there is not really recursive right away. So we're going to focus on the recursive helper method. So that's the method we're going to focus on. Okay, right here. Binary search helper. Let me start by saying what we really want to figure out is the range, right? You can see from and to, right? You can think about this is the initial search space we start with of size n. And you can think about we want to work out exactly what's the running time function when the input size is exactly equal to n. Let's put a question mark. That's something we want to figure out at the top level. And there are different cases for t of n. N could be 0, empty range. N could be 1, we got only one element in the range. Or n can be something larger than 1, in which case we're going to run some recursive call, right? So there are 3 cases basically. So that's why you see 0, 1, and n right here. That's typically the possibility for the input sizes. Let's now look at them one by one. Case number 1. So when from is larger than 2, that means we got empty search space. In that case, we simply say the element cannot be found, just return false, right? In this case, we're going to write the following. We're going to say t, the running time function, when the input size is simply equal to 0. The 0 here corresponds to the fact that from is larger than 2. And what's the corresponding running time? Only a single return, constant, right? Return is a primitive operation, equals 1. 1 here corresponds to the return. And the 0 here returns correspond to the empty range that we're specifying. Okay? Let's now do something very similar. What about the next base case? So here we got else if over here. And this one here, you can see this part here is also constant. Array indexing and also some like relational comparison. That's also constant time. What's the input size? When from is equal to 2. For example, from equal to 2, that's only a single element that we're looking at, right? So the way to formulate it, maybe you already got it in your mind. T here of input size 1 equals just 1, right? So the 1 here corresponds to the primitive operation right here. And the 1 here corresponds to the range of elements, just one element there in the search space. Okay? So also good? So let's fill out what we have got so far. We got 1 here, and also we got 1 here. Okay, 2. Let's not worry about the n case in general, when it's strictly larger than 1. So in which case we have to make some recursive call. If you look at the recursive case over here in the else part, I would divide them into 2 parts. Part number 1, we are making some preprocessing. We want to calculate the middle index. We want to calculate the middle value. That one there we can figure out right away. It's only about assignments, arithmetic, and also assignments, array indexing, constant, right? So for that part, I'm just going to box them over here. That one there, I would just say big O of 1. All right. The whole thing is going to be the t of n that we have to worry about. Let me put it here. The whole thing is going to be the t of size n, not the base case. What about the remaining part here? This is why the if and else if is so important to understand precisely, right? If you look at the if and else if, so here we got either this one here or else if. That means we're going to go to either one of them, but not both. And what's the input size over here? Well, let's now look at the code once more. If you look at here, it's actually from to middle minus 1. That one there tells us we should go to left half. So it's really from to middle minus 1. If the original input size is n, what should be the size of this? n divided by 2, right? Half. So this, if we go for the if branch, the input size is going to be n divided by 2. What about if we go to, let's say, the right half? That'll be middle plus 1 to 2. Middle plus 1 to 2. The size of that also is n divided by 2, just half, right? That one there is also n divided by 2. So we can go to either branch, but not both. When we go to either branch, the running time is just going to be about half of the t of n. Because t of n is about input size n. So we just want to go to t of size n divided by 2. All right? So let's write it down here. So this range over here, as we argue, is of size n divided by 2. And this one here is going to be n divided by 2 as well. So the way to formulate each recursive call is we can safely assume this one here is going to be the time, but on the input size, that's half. And for this one here, it's also going to be running time of the input size being half. All right. So now we are ready to see exactly what t of n should be. Okay. We have this constant preparation, and then we can go either this one or this one, but not both. Right? So the way to put it would be, we can say t of n divided by 2, we can either go to the left or go to right. So this can be left or right. And then the preprocessing job that we're going to do, which would be plus 1. All right? That's how we formulate the mathematical running time function from the code. Right? We're going to do another 1 or 2 examples when we talk about merge sort and also quick sort. So we do have some chances to practice. Let me mention something that's wrong. It would be wrong if you say the running time when size is equal to n will be t of n divided by 2 plus t of n divided by 2 plus 1. Okay, first of all, convince yourself this one here is definitely different from this, right? You can see only one occurrence, but here we got 2 occurrences. This one tells you only making 1 recursive call. But this one tells you making 2 recursive calls no matter what. And this one here is definitely not reflecting the code logic, because we can go to either this or this, but not both. Okay? So this is wrong because the if and else if structure. Okay, I'll just make it brief about the reason. Question?
Sorry, where did the plus 1 come from?
The plus 1? Are you talking about the plus 1 right here? Yeah. Okay, this one comes from every time you make a recursive call, before you make a recursive call. Or put it this way, when you talk about a recursive case, and that you got to do some preprocessing to really calculate where the middle value is. That's the 1. So every time you want to handle for size n, which is not the base case, you got to first of all calculate the middle value and then make a single recursive call. Right? I could have said 1 plus t of n divided by 2. It will be okay too. Yeah. Good? All right, guys, any question until now? So what we have done is the first step, which is to say, given the Java code, we're going to formulate its running time function. The second step is going to be purely math. We're going to take this running time function here, recurrence relation, and solve it. Okay. The way we solve it is by a technique called unwinding or unfolding. And the essence of this approach here is you got to be very cautious about doing some substitution, which I'll show to you. And also you have to be very abstract thinking about identifying the pattern for the sequence, right? I'm going to show you both. Right, let's now try these, okay? I got 0 here, I got 1 here, I got n here, and these are the ones we just spoke about in the previous page, right? We already spoke about them. Let me make some assumption here. Let's say the n over here can be 2 to the 0, 2 to the 1, sorry, not 2 to the 0, 2 to the 0 just be a base case, right? It could be 2 to the 1, 2 to the 2, 2 to the 3, etc. Just easier for us to think about, okay? So what you guys usually see in the math class, assume without loss of generality. Without loss of generality. Let's say n is simply the input size 2 to the x for x larger than or equal to 0. Of course, that will include 1 here and also 2 to the 1 to the 2 and so on. Okay, some assumption aside. If the assumption is not really met, the way you prove it will be very similar, but just a little bit inconvenient. You wouldn't get integer. Let's now do some warm-up exercise. If you can understand how the warm-up exercise should be understood, it should be good for each step. Okay, warm up. Based on this definition over here, can you try to calculate what would be T of n divided by 2 be? All right. I'll give you hints. This number here is the input size. You want to do some pattern matching. Does it really match 0? Does it match 1? Or it can be matching n? That's what you want to think about. N divided by 2, apparently you cannot argue that it's simply 0. Also, you cannot argue that it's simply just 1. Not necessarily. So the safest bet is to go for the n here. You simply replace every occurrence of n here just by n divided by 2. That's what I meant by substitution. All right? So I'm going to substitute every occurrence of n right here by n divided by 2 and see what the outcome is. Okay? Now I'm going to put it here. Will be T of n divided by 2 divided by 2 plus 1. Think about n divided by 2 is here, and then the divided by 2 is exactly the divided by 2 here. And then plus 1 is a plus 1 here. Right? And then you are just going to get T of n divided by 4 plus 1. Are you okay with it? That's the most critical step, I would say. If you can understand that kind of substitution, we're just going to continue doing it until we see the pattern for the unfolding. Right? Any question you got about this unwinding, it's now time to ask before we dive deeper. Okay? Let's now try to solve it. Okay? I will start with the general case. T of n. By definition, I can use this equation here. T of n divided by 2 plus 1. Okay? And then I want to unwind this one here. The way I do it is exactly what we just did for the warm-up exercise. I'm going to substitute every occurrence of n here just by n divided by 2. Okay, that's what I will do. And we know the answer already. Okay? So I'm going to write as follows. This part over here is going to be what I'm going to do for the substitution. And don't forget the plus 1. The plus 1 here comes from the plus 1 here. Okay? And this part here is going to be T of n divided by 4 plus 1. And this part here is what we calculated earlier. Notice that we got plus 1 here and plus 1 here. You should know why. Okay? Let's do one more. Now I want to basically try to calculate what is T of n divided by 4. I want to do one more unfolding. I can do as many as I like, but I just need to see the pattern. And then I'm going to say something like this. Okay, don't forget I got a plus 1 here. And also, I'm going to do this part here. This is what I'm going to unwind into. And the plus 1. The plus 1 here comes from the plus 1 here. The plus 1 here comes from the plus 1 here. All right? What about this part? I'm going to substitute every occurrence of n just by n divided by 4. And here, n divided by 4. Any idea? What should that be? N divided by 8. All right, good. All right, it's going to be t of n divided by 8 plus 1. I think we got enough to see the pattern. Usually, after maybe 1 or 2, or usually 2 or 3, unwinding step, you should be able to see the pattern. You shouldn't need to do more. All right. Let me tell you how you can think of it. The problem is, if I keep doing this, I'm just going to say n divided by 8, n divided by 16, divided by 32. I can just keep going. But that's not going to help me anymore. I want to see how large this number here, the denominator, should really get to so that I can reach the base case. That's really the insight. Because once I reach the base case, I will be able to say it's equal to 1. That's really the idea. Okay? So I want to keep doing this until I can say I got t of 1. That's really what I want to get into. All right? In order to see how I can get to t of 1, let's now observe some pattern here. By the way, I simply just cannot say t of 1 being the final running time, because t of 1 is simply just 1. In which case, I cannot conclude binary search is a constant time operation. No, I cannot say that. Right? It's not that cheap. Okay? Because you got all the plus 1 right here, all the plus 1 here, all the plus 1 right here. So how many plus 1s I really end up having is really going to determine the final running time. Okay? I'm going to give you guys some hints. So what I want to see is I'm going to get a bunch of plus 1. And the question is, how many? Because the pattern, at least I can see, I always got some plus 1s. So eventually, if I got this one reduced to t1, I also got a bunch of plus 1. But I don't know how many. In order to see how many, I need to identify the pattern. I'll give you guys some hints. To see the pattern, you want to pay attention to the denominator, 2, 4, and 8. Okay, anybody see the pattern here? You want to see the relationship between the denominator and also how many plus 1s you have. If you can identify some relation there, you're basically done. Anyone? Yeah. 2 to the... So you're saying exponent will correspond to how many 1s you have? Is that what you're saying? Or the 1s determine the exponent. Okay. Anybody else? Diago?
Take the log of the denominator, you'll get the number of 1s. So for example, for 9, if you take the log of 8, that's log 2 of 8, that's 3, and that corresponds to the number of 1s.
Getting somewhere. Okay, good. Let me make it more precise. Very nice. Huh? What's x? So let's see this. The x over here. However, this x is only for n, right? So we're not being specific to each line over here. But you're getting somewhere. It's about something about exponent, something about log n, but we're going to see how to put everything together. Okay? Let's see this. This denominator here, it is 2 to the 1. This one over here is 2 to the 2. And this one over here is 2 to the 3. The pattern goes like this. The exponent suggests how many plus 1 you have. Exponent is 1. You got only 1 plus 1. When the exponent is actually 2, you got 1 plus 1 and another plus 1. You got 2 plus 1s. And when the exponent is actually equal to 3, you got plus 1, and also plus 1. You got 3 plus 1s. That's the pattern. Okay? So now we want to figure out in order to really get to this particular one here, how can we rewrite it in a way we can see the exponent? So that's our challenge. All right? Can you follow the logic here? Okay. So now I'm going to leave it aside here. Okay, 1 here. So I'm going to write here. So 1 here, would you agree, is n divided by n. I want to get this part here matching n. All right? And then I want to somehow rewrite this n here to 2 to the power of something. If I can figure out the exponent here relative to the n here, then I will get the number plus 1s based on the pattern. N divided by 2 to the power of something. If I can figure out what the question mark is, that one will tell me how many plus 1s I have right here. Guys, what should this be? This will be something you learn from the calculus course. It's a property. Well, if I got, for example, n equals 8, right? If I say 8 divided by 2 to the power of something is going to be equal to 1. What should that be? Log 8? Yeah? Okay, good. Right? So if you think about it, this is n, this is log n. Right? Think about the property, right? I'm pretty sure you have seen that before. Basic. Okay? All right, so that's just a side for you to recall. So the question mark over here really is log n. All right? Because that one there is just going to, because 2 to the power of log n is just going to give you n. Okay? So now we can now answer for this particular question. How many plus 1s do we have? In order to reduce all the way to 1, we need to say n divided by 2 to the power log n. So this one here really matches the pattern, log n. That's really the exponent, right? That tells me the number of plus 1 here should be exactly log n. Log n. All right, let's now finish off. This one here is going to be t of 1 is just 1. Plus, we got log n plus 1s, which would be just log n. So this is the final running time for binary search. It's a log n time algorithm. Okay? Let me recap over here. Of course, there's quite a bit of math over here you have to get used to. Okay, let me recap. We start with the Java code, in which case you're going to assign each portion over here to the corresponding part for the recurrence relation, depending on the input size. Can be 0, can be 1, can be n. And then once you get that recurrence relation, you're going to solve it by unfolding it. And then when you unfold it, usually it will take about maybe either 1 step and 2 steps. That should be enough for you to see the pattern. The idea would be you want to reduce the t function here all the way to t of 1, the base case. And then once you get there, you want to see what the pattern will suggest, how many plus 1 you have in this particular case. That'll be log n, as we show you right here. So that's why it's a log n algorithm. All right? Any question? Take some time to think about it. This one is still like an easier one compared with the MergeSort and QuickSort. We're going to do MergeSort unfolding maybe on Thursday. But today we're also going to talk about MergeSort in general. Okay? All right, so if you're okay with the binary search, let's now move on to something called MergeSort. Okay? If you look at the slides, you will see that right here. So that's something we'll talk about for binary search recurrence relation. And also, that's the unfolding I kind of showed to you from scratch. You can also take a look at the slides. MergeSort. We are basically given the same computational problem, which we spoke about before. The precondition for sorting is none. You don't really assume any structure on the input array. It can be completely sorted or can be completely unsorted, right? Just anything. And then we want to make sure it's sorted, for example, in the non-descending order, which we spoke about earlier in the course, right? And we're going to talk about 2 sorting algorithms, MergeSort and QuickSort. Today is mainly the MergeSort. We'll talk about QuickSort as well, briefly, on Thursday. And for the MergeSort, I'm going to talk about, first of all, some general idea about the different steps, different phases. And I'm going to highlight about which step should be a little bit more expensive, which one should be cheaper. And then I'll show you the Java code. And then we'll talk about some tracing. Okay, we'll see how far we can go. Right, let's start with some idea. Okay. So I'm going to just make it a little bit smaller. Okay, that should be good. And I'm going to use a similar color convention as I did for selection sort, insertion sort. Okay. Let's say we start with a linear sequence. Could be array list, could be array, can be syncly linked list, doesn't matter. Okay. Let's say we start with a list that's complete, that's unsorted. Consider. Okay. Start with something that's unsorted. Of course, eventually we want to get something that's sorted, but we'll see how to get there. For the merge sort, there will be two steps you have to watch out for. I'll write them down first. I'll explain them as we go. The first step is called split. The second step is called merge. The merge is really where the sorting name comes from, MergeSort. Right? We'll see exactly what that means. We do something called split. We simply split the list into half, exactly halfway. So we get two different lists. So we're going to get so-called left half, and also we get another half. Okay, I'll call this the left, I'll call this the right. And of course, both of them are still unsorted. Unsorted, unsorted. Okay, two separate lists, just split. And if you think about the size, so you can imagine we are trying to call the sort method on this particular input of size n. So this size over here is going to be n over 2. This is going to be n over 2, exactly half. We haven't done any sorting just yet. And then we're going to call the sort recursively. Okay, so this step over here, oh, by the way, this step here is called split. And this one here is going to sort recursively. We're going to make two independent recursive call on the sort. Two independent. There's no choice. You got to do two exactly. So we're going to, first of all, let me copy these two input. Okay. And then let me just put the right here. Okay. So imagine that we're going to call the sort on the left. Also, we're going to call the sort on the right. And sort on the right. So this is one recursive call. This is another recursive call, right? Separately. Each one of them, we can trust on the recursion. It's going to return back to us some sorted list individually. Okay? And then the recursion result is going to give us two sorted lists. So results are two sorted lists. So what I would do is I'm going to, so this will be the left. Oh, you know what? Let me do it this way to make it more explicit. The same input list, but after the recursion, right, left and right, they are going to change to be sorted. Oh, there we go. Okay, left and right. Once more, we split into two unsorted lists. Make a recursive call on each one of them, and then we trust that recursion is going to return back to us two sorted lists. But we are not done yet. What we expect to see is a single sorted list of size n. Now I only got two sorted lists. Each one of them is of size n divided by 2. So here comes the most critical step for MergeSort. Once I got the two sorted lists back, I should merge them. And this one should sound familiar to you. You remember back in assignment number 2, there is a task there to merge two sorted lists. That's exactly what this will do. So in some way, you already know how to do this one here. So that will make it a little bit easier when I explain to you the Java code. Okay? So this one here is going to give you just one single sorted list back. And this will be of size n. And that one there is completely, oh, sorry, beg your pardon. That one's completely sorted, okay? So these are the conceptual steps you want to know in order to understand MergeSort. And when you look at the Java code, it corresponds to exactly this kind of structure, this kind of flow, okay? And this part here is called merge. Right, let me say a little bit more about the recursion here, so you will appreciate a little bit more when we get to the code itself. When I say sort recursively, so each recursive call is going to do two things, split and merge. Let me talk about them a little bit over here. So each recursive call is going to do two things. Number one is going to simply do the split, right? Pretty much like you just split the whatever list it is into half, okay? So you're going to do the split. And let me be more precise about the split. In the beginning, if you're given some list of size n, it's going to split into two lists of size n divided by 2 and over 2, half. And then another split could be you're given some input size of n divided by 2, you're going to split into n divided by 4, n divided by 4, right? Exactly half. And this split will actually simply go on until you go to, if you got size 2 list, and then you're going to split them into 1 and 1. So on. Split basically just keep splitting until you can reach the base case, in which the list size is simply just 1 and 1. By default, a list of size 1 is automatically sorted, okay? So think about these two. This one here is sorted, and this one is sorted. Once you reach the base case, you should really try merging. Merge only happens after you have done the splitting, okay? What about the merge? The merge is going to be completely the opposite idea. For the merge, over here, we're going to say if you got two sorted lists of size 1, you're going to merge them into size 2. If you got two sorted lists of size 2, you're going to merge them into 4. And then go on. Let's say if you got n divided by 4, n divided by 4, you're going to merge them into n divided by 2. If you got n divided by 2, n divided by 2, you're going to merge them into the final n. So this is the final outcome that we are looking for, okay, the merge. Okay. So for these two elaboration over here, you may appreciate it a little bit more once we see the tracing, but I want to write them down right away, right? Okay. And I want to mention very quickly about the running time for each one of them. Split is very easy because there's no sorting involved. You just split them. It's a constant time operation. On the other hand, for merge, as we will see, you will actually have to keep some pointers about each sequence there for left and right and go a linear scan on them. So that'll be a linear time algorithm, which I'll show to you a little bit more detail. Big O, off, and right here. All right, so that's just some conceptual sketch and like a visual introduction to MergeSort. Okay, so what's left for today, I'm gonna go over the Java code with you in very much detail about MergeSort, and then we're gonna do some tracing. Okay, that's what we'll do. Okay. Okay. Why don't we take a short break by taking attendance, and then we'll do that. Okay. All right. So let's now dive into the Java code for MergeSort. Okay. So one very simple exercise for you guys to try is this part over here is about the recursive case for MergeSort, the general case. All the steps over here correspond to exactly the visual sketch that we did before the break. That's something for you to double check. Exactly right. All right. But now let's analyze the running time. Sorry, not running time. Just understand the logic first. We'll do runtime on Thursday. Okay. Now I just want to understand the Java code and also do some tracing, and that'll be it. Let's start by looking at the base cases. Okay. So this part here, there are two base cases, here and here. Okay. So these are the two base cases. So basically, base case number 1, when the size of the list is actually 0, in which case the list is already sorted, right? And also, if the list size is equal to 1, it's also sorted. So in that way, nothing to do, really. Nothing else complicated to do, okay? So base cases are very trivial. What we need to look at is actually right here, okay? Right here, right? So what we do is we first of all want to find the middle part so we can do the split, right? We find the middle so we can do the split. The way to do the split is by using a sublist method from array list, which we assume is a very efficient operation. So we assume that, just for I'm going to point out to you, for sublist, we assume that it's going to be a constant time operation. We assume that, okay? And that one there is simply going to split the list into the left and the right. And this corresponds to the left and the right. That's unsorted, all right? And we're going to make the recursive call on the left, the recursive call on the right. It's going to return sorted left and sorted right. And this one corresponds to the sorted left and sorted right. All right? And then we're going to call the merge method, which is a helper method I'm going to dive into. The merge is going to take the sorted left and sorted right, return some sorted list. And the sorted list is exactly this one here that we're going to get. Okay? Eventually, we're going to return the sorted list. So the Java code itself doesn't require many lines. It corresponds to exactly what I described before the break about the conceptual sketch. But let's now dive a little bit more into the merge routine. Okay, right here. Okay. And let's now do some very quick tracing together, and that's the merge. So most of the detail I will need you guys to really follow up, by yourself. It's just a simple Java code. There's not even nested loop. So I'm going to explain to you in a high level how it's going to work. We're going to keep two integer like a pointers, I and j. I is going to tell us where we are in the left unsorted list. It's going to be on the left list. And j here is going to be on the right list. And since we are calling the merge on the sorted left and sorted right, so there is some precondition about the merge. Okay, I'm going to write it down explicitly. So the precondition for the merge is the left and the right list are sorted. If they are not sorted, there's no way you can run this algorithm to make another larger sorted list, right? That's really important for you to remember. Okay, let me highlight it right here. Okay, they're sorted. You can see the left here is sorted, and also the right here is sorted. Now I'm going to use I and j to show you exactly how that works. Okay, so we got I here in the beginning, and also we got j here in the beginning. The idea is, for each iteration, you're going to compare where I is pointing to, and also where j is pointing to, and choose the one that is smaller, and put that into the final sorted list. You got to keep doing this. Here we got I pointing to here, and j pointing to here. Compare 17 and 24. Which one is smaller? 17. I'll take this element and put that into the merge list. Okay. So I'm going to put 17 right here. At the same time, I'm going to move the j pointer to the next element. Second iteration. Compare 24 and 31. I should take 24 because that's smaller, right? So I'm going to, number one, I'm going to put 24 here, and then move the I pointer to exactly over here. So what you will see in the code is we will either do I++ or do j++. Right? That's something you will see in the code. Let's move on. So now we got either 31 or 45. We should take 31, right? That's smaller. So I'm going to put 31 here and then move that to the next one. And then we compare 45 to 50. We should take 45. So I'm going to put 45 right here and then move that into right here, right? And then we compare 63 and 50. We should take 50. In which case, I'm going to put 50 over here and move this guy here to the last element here. And then I compare 63 and 96. I should take 63. I'll put 63 here, and then move that to the last element. And then I compare 96 and 85. I should take 85. If I put 85 here, now here comes a very critical point for the merge. Because after this, I'm going to move the I pointer to one beyond the array. So now I is not pointing to any valid index anymore. So there is no point to really go into the left list anymore. So we say that at this point here, the left list has been exhausted. Okay, that's the terminology. So at this point over here, we say the left list is exhausted. If one of the lists is exhausted, which can be the left or the right, the other one, you don't need to do any more comparison. Wherever J is pointing to, just append the rest of the list into the sorted list. That's all you got to do. Okay. So at this point, I can simply say, because it's now pointing to 96, I can put 96 right here. Okay. If there are more elements after this, maybe more, I can just append all of them to the end of the merged list. That's going to work too. Okay. So there are really two phases over here for the merge. Phase number one, you want to keep comparing I and J where they're pointing to and put it into the merged list until one of the lists is exhausted. And phase number two, whatever list is not exhausted, you're going to append the remaining part to the merged list. Okay, so these are the two phases. And we're going to see the running time for merge because that one is not recursive. Okay. Let's now take a look. Okay. Phase number one is right here, the while loop. Right here. And we are based, let me just say, yeah, exactly. So this one here is going to compare I and J. We can either try to add it to the left or add it to, we can either try to add from the left or add from the right. Okay. To start with, you can see for this part over here, and also for this part over here, each one of them is just going to be a constant time operation. We assume that whenever you want to add to the end of the array list, it's going to be big of 1. We assume that. Okay? So they are simply big of 1. Okay, we can write it down first. And then we can also look at the condition right here. Okay, the while loop condition. Okay? So this is to say, if this condition is true, we're going to keep comparing I and J value, right? So what does it really mean when we can exit from the loop? That's really important, the logical negation of the condition here. I'm going to write it down here. So this one tells you you're going to exit from the while loop when the negation of this conjunction here is true. We can apply De Morgan, right? Remember we talked about De Morgan. So it's going to be I larger than or equal to L dot size, or J larger than or equal to R dot size. And for the example we just ran, you can see I here was one off the largest index, which is exactly L dot size. Okay, that's one example. Of course, if the right list is exhausted, it will be the other way, right? So this one just tells you when to exit from the loop. So having this insight here, we want to know how many iterations do we really have for this first phase. Okay, I'm going to write it aside. So in the first phase, we are trying to exhaust either the left or the right. Exhaust. Either the left list or the right list. Let's say, for example, we exhaust the left list, like we did in the example. So for example, let's say L, the left list is exhausted. How many iterations have we run really? Approximately. You can think in this way. The I value is right now, for example, let's say 1, 2, 3, exactly 4, right? And the J value at this point over here is also 4. That's roughly how many comparisons we have done, right? Because that's really about the values that we have already put into the merged list. How many elements are there correspond to how many comparisons we have done and put into the merged list. Okay, so you can think about that one approximately is simply equal to I plus J iterations so far. we have done so many comparisons so far, and we have already exhausted one of the lists. So specifically, since we assume L is already exhausted, so I here is going to correspond to just the length of the left. Okay, so let's now put something aside. I here, in this particular case, because we assume L is exhausted, so it will just be L dot size. Right? Think about this kind of argument here. It's really important about understanding the merge routine. All right, and then we are now done with the first phase, and then for the second phase, it's kind of straightforward. So we can either try to exhaust we try to exhaust the remaining list, basically. Okay, either we go for this one here, we go for this one here, right? So I'll put it here. We try to simply append the remaining elements from the unexhausted list. Let's say for the example that we just went over, when we have already exhausted the left, we have only gone to this part of the list, right? So that means we still have one more to be filled in. So that'll be the remaining part for the right. That's unexhausted. How many exactly is there, roughly? Because the J value is already here, that tells us we got one more to really append into the merged list. So it's approximately about the size of the right minus the value of the J. That tells us how many are remaining. Think about J is about how many we have gone so far. And the size is how many in total you should really go. So fill the gap. Okay, calculate the gap. So here, for the star star, you're going to append the remaining elements from, in this case, the right. Approximately, it should be R dot size minus J. Right? So you can see R dot size in this case is 4. Minus J, 3, you get 1. That means you got one more element to really append. In that case, it will take one iteration more to really append it. Okay? So we have basically analyzed separately this loop here and this loop here, different phases. But in total, how many iterations do we need? Because we know that, let me just do one more. You can see here for the add over here, and also for the add over here, the worst case for each one of them is simply constant. So all we gotta figure out is how many iterations in total we gotta do. Okay? So total number of iterations, let me write better, for the merge. We're going to add up two numbers. Let's add up this number here and also add up this number here. Okay, let's add them up together. It's going to be I plus j, which we know L dot size is equal to I, right? That's what we assume. It's going to be L dot size plus j plus R dot size minus j. R dot size minus j. And you can see nicely, plus j minus j cancel out. It'll be L dot size plus R dot size. All right, so that's a very important conclusion from here. What does that mean? That simply means if you actually got two lists over here, the number of iteration you will need in order to get a merged list will be exactly the size of the left and the size of the right. Very intuitive, but to really argue that mathematically, that's what you got to do to really figure out. Okay, that's what I just have shown to you. Okay, so total running time for merge. So the running time for merge alone, it will be big O of, you can see each iteration is going to take big O of 1, right? It's going to be 1 times the L dot size plus r.size. And let's see one example. Let's say when you actually try to merge over here, L.size is n over 2. R.size is n over 2. What's in total? N. So that's why we said intuitively, merge is a linear time operation. Okay? Okay. I think this one will be good enough for now, and then I will elaborate that on a little bit more. Okay? On Thursday. Okay? Okay, let me also write it down here, so that could be a little bit. Okay, so the merge method here, our conclusion is going to be the big O of L.size plus R.size. All right, guys, any questions? Diego.
So is the sort method being called in code part of the list class?
The sort?
Yeah. When you call sorted that, you call sort that.
Mm-hmm. Oh, okay. You mean the sort here?
Yeah.
Okay. So here we didn't really say which class we're defining. You can think about you may have some sort application class in which you try to define the sort method. But here we're just talking about just the method itself. You can put in whatever application class you like.
Okay,
But yeah, so yeah, exactly. So you can think about this sort method here. We're just making use of array list to use the add and also sub list. That's all we're doing. Mm-hmm. Yeah. All right. Any question about the Java code here? We're good. Okay. Let me pause one more time. All right, so now we are done with kind of analyzing the Java code. And on Thursday, I'm going to talk about the running time. But one more thing for today. I want to trace one example input together with you about MergeSort, so you can see exactly how that works from beginning until the end. Let's see exactly how we can do the split and merge. Basically, you split from the top all the way to the bottom once you reach the base case, and then you kind of merge all the way back onto back to the top. All right. So let's see this. So in the beginning, we got some list that's unsorted. Right here. Right? This one is unsorted. And then we try to do some split right here, and we try to do split right here, and split. Let me just do better. Split here and split here. And then what we will get is we're going to get 85, 24, 63, and 45. You can think about this as a middle line here, right? We can calculate the middle index, okay? And then we got 17, 31, 96, and also 50. And notice that both lists are unsorted. You just split. And then we'll do another split. Split this one here into 2. And also split this one here into 2. Okay, let's see what we're going to get. So for this one here, you're going to get You're going to get 85, 24, and then 63, 45. And also 17, 31, 96, and 50. Each one of them is also unsorted. We are now getting back to the base case very quickly. Okay? And I'm going to do further split. Split here, split here, split here, and split here. So what we're going to get is we're going to get 85, 24, 63, 45, 17, 31, 96, and 50. A list of size 1 is automatically sorted. So you can think about each of the lists right here is sorted. Sorted, sorted. So until this point, we're done with split. What we do is we're going to merge all the way bottom up. Okay. So what we do is we're going to merge. Let's start by merge these two. If I want to merge these two, I should really get 24 and 85. Right? You can think about this would be some merge. And then I'm going to merge these two. That one is going to give me 45 and 63. And if I try to merge these two, it's going to give me 1731. Yep. It's going to be 17 and 31. And try to merge these two, it's going to be 50 and 96. And now you can see that individually, these are sorted. All right. We got to do more merge. So now you can see we go from size 1 to 2. Size 1 to 2, right? If you go back to where I said earlier, I want to point out very quickly. You can see earlier when I said the inside, when I get 1 and 1 to 2, and 2 and 2 to 4, right? Exactly what I said earlier, right? Just want to point out to you. We're almost done. Bear with me. So now we're going to merge these two. So we're going to merge again over here. So there'll be another merge. That one's going to give me 24, and then 45, and then 63, and then 85. That one is sorted. And then I'm going to merge these two. That one is going to give me 17, 31, and then 50, and then 96. Okay. Now, final merge. So this is the case where you can see that you actually got, okay, let me just, okay, this is the final merge that we're going to do. This one here, I'm basically trying to merge n over 2 and also n over 2, combine them into n. The size of the left is n over 2. The size of the right is n over 2. Together, we're going to need big O of n to really merge them, right? And let's do it. So this one here is going to be crossed out. And what we'll get is, we're going to get, 17, 24, 31, and then 45, and 50, 63, 85, and 96, right? So that will be the final sorted list. So we go from the unsorted list, we split all the way down to the bottom and merge all the way back up to get a sorted list. That's a merge sort. All right, so before Thursday, just give me 1 minute, I'll let you go earlier today. Before Thursday, this is what you should do to get yourself ready. You want to review about this merge sort big idea, especially the inside I mentioned about here. And then look at the Java code again, just to see exactly how they work, especially how we judge about the running time for the merge, which I'm going to assume for Thursday. And then look at the tracing over here to get more insight. And then we're going to try to solve the recurrence relation for the merge sort, which is going to be more challenging than the one for binary search. All right. Thank you so much, and then I'll see you on Thursday.